It is clear to everyone the importance of studying protein structure and how NMR and X-ray crystallography are the most powerful methods to study protein structure at atomic resolution. However, why we interested in NMR is because NMR is the only method that allows the determination of 3D dimensional structures of protein molecules in the solution phase. It is not limited to proteins that crystallize well for X-ray crystallography. NMR spectroscopy is often the only way to obtain high-resolution information on partially or wholly intrinsically unstructured proteins. And of course, NMR is very useful method for studying kinetics. However, NMR also has a few limitations. One of them is the protein size, which is limited for proteins up to 35 kilodalton. And structure determination can sometimes fail in solution due to aggregation or protein dynamics and reduced solubility of protein sample. As soon as you walk into any NMR room, you pretty much see something very similar to this picture, which shows any NMR spectrometer inside. Any NMR room is basically consisted of three parts. Superconducting magnets on the left, NMR console, and the computer workstation. And once your NMR sample is prepared, you can just insert it from the bore, which is located on the top of the superconducting magnet, and use the computer to inject the sample in and start recording the spectrum. Superconducting magnet has different parts. On the top is the bore, which is the hollow part inside the NMR machine where you insert your NMR sample tube. And there is liquid nitrogen jacket and liquid helium jacket. And the reason we do have these two is because liquid helium is it's because of its low boiling point is used in many cryogenic systems when temperature below the boiling point of nitrogen is needed. Liquid helium is used in here to keep the magnet cold, and the liquid helium is protected by a jacket of liquid nitrogen, which is less expensive and more readily available liquid gas in order to prevent the liquid helium from boiling off into the atmosphere. When sample is placed in a magnetic field, a radio frequency generated then irradiates the sample with short pulses of radiation. The radio frequency pulse is given to the sample through transmitter coil, which excite the sample, and when the nuclei fall back to their lower state energy, the detector then measures the energy released through the receiver coil, which then a nuclear magnetic resonance response, or which we call free induction decay, or FID, can be obtained. FID can be easily then transformed into spectrum by Fourier transform. A Fourier transform is carried out to extract the frequency domain spectrum from a raw time domain FID. Spectrum from a single FID has low signal to noise ratio, but it can be improved with averaging of repeated acquisitions. A good hydrogen NMR spectra for example, can be acquired with 16 repeats, which takes only minutes. However, for elements heavier than hydrogen, the relaxation time is obviously longer, and the acquisition of quantitative heavy element spectra can be time consuming and taking minutes to hours. NMR sample tube, shown on the left, spins inside the superconducting magnet, and spinning the sample is usually necessary to average out diffusional motion. Just to have a sense of how powerful NMR magnets are, you can see a comparison of magnetic field strength between different sources in this table. Magnetic field strength is defined by unit Tesla. It is common to refer to for example, 1400 Tesla magnet as a 600 megahertz magnet, since hydrogen is the most common nucleus detected. However, different nuclei will resonate at different frequencies at this field of strength in proportion to their nuclear magnetic moments. For example, you can see for 600 NMR, nitrogen resonates at 60 megahertz frequency and carbon resonates at 150 megahertz. For the last one, as a practice, you can calculate the frequency of hydrogen, nitrogen, and carbon for a magnetic field strength of 25.9 Tesla. This is the most powerful NMR made by Bruker and now is installed in the Magnetic Resonance Center at University of Florence, Italy. Here I show the process of recording an NMR spectrum for a protein sample. Once the protein is purified, it can be dissolved in a proper NMR buffer with an appropriate pH, and then it can be transferred into NMR tube, and then it can be transferred into the spectrometer. Once it's transferred into the spectrometer, the acquisition parameters can be set up, and recording can start. And once the acquisition is finished, the next step is to process that acquisition data, which, depending on whether it's 2D or 3D or even 1D experiment, different processing can be applied. Resolution of NMR spectrum directly depends on magnetic field strength. For example, the figure that I've shown here on the left panel has used a low magnetic field and has 80% peak overlap, whereas using higher magnetic fields can resolve all the overlap peaks and produce better signal to noise ratio. However, using a higher magnetic field is more expensive. As you can see on the right figure, for example, using a 1 gigahertz NMR can be twice more expensive than using a 800 megahertz NMR. However, sometimes you need to use a higher magnetic field because you've got so many cross peaks that are overlapped, and the only way to improve your signal to noise ratio is to use a higher magnetic field. For instance, for bigger proteins, bigger than 35 or 40 kilodalton, you definitely have to go to higher magnetic field. Otherwise, you won't have the resolution that you need to see all the cross peaks completely resolved. This is the one that was published last year. This figure is from 1.2 gigahertz NMR, which shows using TROSY spectra of a sample, which is shown in red, it can be significantly improved by using a higher magnetic field, which is shown in blue. The vast majority of molecules in a solution are solvent molecules, and most regular solvent for proteins is water and contains NMR active protons. In order to avoid detecting only signals from solvent hydrogen atoms, different water suppression techniques can be used. A few of them are listed here. For example, if a pre-saturation water suppression technique is used, as you can see on the left, it can significantly reduce the peak of water, which is around 4.85 ppm. Apart from water suppression techniques that has to definitely be used, we use 5 to 10% deuterium with our NMR sample to lock frequency and define 0 ppm. Modern NMR spectrometers measure the deuterium absorption of the solvent to stabilize the magnetic field strength. That's why we need to use 5 to 10% deuterium always to lock the frequency. Other nuclei can also be used for this purpose, but just deuterium is the most convenient. And we also use deuterium to define 0 ppm. The difference between deuterium frequency and 0 ppm TMS is well known, and modern spectrometers can lock onto the deuterium signal, so the addition of an internal reference like TMS into your sample is not usually required. pH of NMR sample is also very important because amide proton can exchange in different pHs differently. So in practice, the pH values for protein sample for NMR is usually is kept below 7.5 to avoid fast exchange rates of amide protons. J coupling or scalar coupling, which is a special case of spin-spin coupling between NMR active nuclei, arises from the interaction of different spin states through the chemical bonds of a molecule, and results in splitting of NMR signal. Coupling to N equivalent spin half nuclei splits the signal into a N+1 multiplet with intensity ratios following the Pascal's triangle, which you can see on the table. Coupling to two different spin half nuclei with significantly different coupling constant will lead to a doublet of doublets. For example, you can see a 1D spectrum of for ethanol, and for example for CH2, which is shown in green, because it has 3 hydrogens nearby. You see 3 plus 1, 4, and then will be, which is 1, 3, 3, 1 intensity ratio. See 1, the smallest one, 3, 3 in the middle, and 1 after. Same for CH3 methyl group. It has a CH2 nearby, and it has two neighboring hydrogens, which makes it 2 + 1, 3, and a triplet. And the intensity ratio will be 1, 1, 1 to 1. Different 2D NMR spectroscopy can be used for protein samples, and it can be categorized into homonuclear through-bond correlation methods, heteronuclear through-bond correlation methods, and through space correlation methods. And the most commonly used one is heteronuclear single quantum correlation spectroscopy, or HSQC. N15 HSQC 2D NMR spectroscopy is the most frequently measured NMR spectrum for protein samples. In N15 HSQC, with the N15 labeled protein, one signal is expected for each nitrogen atoms in the protein backbone, with the exceptions of proline, which has no amide hydrogens due to the cyclic nature of its backbone. Some amino acids show side chain nitrogen-hydrogen cross-peaks in HSQC as well. The N15 HSQC is often referred to as the fingerprint of a protein, because each protein has a unique pattern of signal positions, multiple conformations, and sample heterogeneity can be investigated by evaluating whether the expected